In this video, we'll continue our discussion of finding extrema, extending our understanding from relative maximums to absolute maximums. I'm going to go back and do a Calc 1 problem to remind us, and then we'll look at a Calc 2 problem and relate the two. Find the absolute extrema of this function, and notice they gave us an interval. So there was a couple things. To find the extrema given the calculus method, just the relative extrema, I'd find my first derivative. So the first derivative of that function is 2x minus 2, right? And then you guys would set this equal to 0 and solve. If I set it, I get a 1. Set and solve, I get x equals 1. So I'm going to plug that into my function. I got f of 1. I plug that in. 1 squared is 1, minus 2 is negative 1, plus 9 is 8. But I also have to check my bounds because we're doing absolute. Remember, absolute means everything. As long as it's on a closed region, we can find an absolute max and min. So f of negative 4, if I plug that in, right, I'm going to think about this one. Negative 4 squared minus 2, negative 4 plus 9. I got 16 plus 8 plus 9. That is 16, 17 to 33. So that definitely is going to be an absolute max if nothing changes between those two. But I need to figure out the other bound, which is going to be a 7. So I got 7 squared minus 2 times 7 plus 9. It's 49 minus 14 plus 9. That is 39 minus 4 is 35 plus 9, which is what? 44. So we have absolute max of 44 at x equals 7 and an absolute minimum of 8 at x equals 1. So what is going to happen in 3 dimensions with boundaries? Well, it's got to be a closed region, which means I have some kind of open area with a region. I'm going to actually have to check all the boundaries, which has an infinite number of points. So let's figure out how to actually do that. So this is what it looks like in 2 space. Let's take a look at 3 space. We're going to have to check our normal extrema, and then we're going to have to check our boundaries. So we have absolute extrema of this function over that rectangle. So that rectangle, hopefully you can see it. It's a 4 by 2 rectangle, 4 in the direction of x, 2 in the direction of y. So I'm going to draw this region to help with our understanding because we're going to have to check each one. All right, so here's my graph, and we don't have to do very much to it. We need more x's than y's. There is my rectangle. I can just hit it up in a dotted form. There we go. There's my rectangle, as good as it's going to get. Okay, so the first thing we're going to do is we treat it like a normal extrema problem. Okay, let's do that. So I need to find my x partial. So I got 2x plus y. And then I got to find my y partial, which is going to be 2y plus x. We're going to set those equal to 0 to create a system. Okay, so I'm going to write down my system here. I got 2x plus y equals 0. I also got x plus 2y equals 0. I'm going to multiply and get rid of things. I'm going to multiply the top equation by negative 2. You can see I don't think anything's going to work here, right? So let's multiply by negative 2. So I get 2x plus y equals 0 on top. And then I'm going to have times negative 2. It does work out for us. We get a negative 4y equals 0. If I add down now, I got negative 3y equals 0, which means y is equal to 0. Right? If I plug that in back to the equation, that also tells me x is equal to 0. So that is a value I'm going to need to check. So I'm going to put critical point 0, 0. And I got to find the other ones. Okay, I'm going to label these lines. We're about to go off to an extension, a decent amount of work here. We have to check every single boundary here. So I have the innermost. I know at 0, 0 is a critical point, so that could be an absolute max or min. We're going to have to plug that in to check. Now for line 1, I'm going to write some silly things. Y, the first thing makes sense. Y is always 1, and x is always just going to be an x, because for this line right here, we get all those x's that are in between there, and then all the y's are 1. I'm going to take this now and plug it into my function. So my function is going to become x1, and I'm going to plug those in. So I got x squared plus y, x squared plus x, because I'm plugging in 1 for y, plus 1. This is now my Calc 1 problem. It's just f of x equals x squared plus x plus 1. And I know that's on the boundary from -2 to 2, just like the problem we just did. So I use my calculus to find the points inside if there are any. I set this equal to 0, and I get x is -1/2. So I got to check 3 things here. I got to check f of -2, f of 2, and f of -1/2 just into the function that we just made up here. So if I plug in -2, -2 squared plus -2 plus 1, I got 4 minus 2 plus 1, which is 3. If I plug in a +2, the only thing that's going to change is there, which I get a 7. And then now I got to think about 1/2, -1/2 squared, plus -1/2 plus 1. All right, we get a 1/4 minus 1/2 plus 1. And then a -1/4 plus 1. And then that's going to give me a +3/4. All right. That only provides me values for that line there for 1. Okay, so there's 1. Let's do 2. Those are our outputs. We have those now. So those critical points would be, let's go over here and add to our list. It's going to be -2, 3, or -2, 1. Sorry, because y is 1. The outputs are what we got there, 2, 1, and 3, or -1/2, 1. There we go. So that's from that one. Now let's do line 2. Line 2 is over here. This is going to be x is always 2, and then y is y. I just write that just to help me what I'm about to plug in. This is f of 2y, and I plug in, okay, I'm going to have y squared plus 2y plus 4. Okay, the calculus tells me now that f prime of y is equal to 2y plus 2. I set that equal to 0, and we get y is -1. So we're going to need now, and then this is the on the boundary from -2 to 2. I lied to you guys. -1 to 1. So I need to plug in -1. I need to plug in 1. And I need to plug in the one I just came up with, which was -1. I don't need to do that again. So I don't need to do it twice. Plugging in 1, I got 1 plus 2 plus 4, which is 7. That's here, not on that. That's +1. Plugging in -1, I got 1 minus 2 is -1. I got a 3. So we have more critical points here. We just figured out what their outputs were. Okay, we got -1, 2, 2, -1, because the x was 2, -1, and then 2, 1. So we have 6 critical points. We have already calculated, thankfully, though, how to calculate that. Okay, so there's line 2. Let me shrink these up. Thanks for being patient. Watching me struggle with an iPad. There we go. All right, so there's 1 and 2. Let me shrink these because I need more room. All right, let's do 3. So for line 3, that was the line on the bottom there. I know y is -1 and x is x. So I'm going to get f of x -1. And I get x squared minus x plus 1. All right, so that means f of x is equal to x squared minus x plus 1. And we're concerned with the interval -2 to 2. So using Calc 1, we'll find our first derivative. We set it equal to 0. So x is equal to 1 over 2. So we're going to plug in now -2, 2, and f is 1/2 into our function there. So plugging in -2, I got 4 plus 2, 6, 7, okay? Plugging in a positive 0 at 4 minus 2 is 2 plus 1 is 3. And then the half I'm going to write down 1/2 squared minus 1/2 plus 1. I got 1/4 minus 1/2 plus 1. You can use calculator if you need. I got 1/4 plus 1. So this is 3/4. All right, so we have those critical points. I'm going to go ahead and add them to the list. I already have the outputs, trying to do the work in all spots. So we got the point -2, -1, +2, -1, and then the third point was 1/2, 3/4. And not 3/4, -1. Because the y, I keep trying to want to put my z there, but those are just the y's that we came up with. Okay, so there's 3. Let's do 4. All right, that was going to be x is -2, y is y. So we got f of -2y. All right, that's going to be y squared minus 2y plus 4. And that interval is going to be from -1 to +1 in the y. All right, so f prime of y is 2y minus 2. I set that equal to 0, and I get y is equal to 1. So we have a few points to check here. F of -1, f of 1. I plug those into the function right above. -1 squared is 1. That's a +2, though, so 3. So I get a 7. Plugging in a +1, I get 1. -1, I get 3. That adds some more critical points, so I'll list them. I got -2, -1, and I got -2, 1. So I will need to check all of those points, but we have all of the outputs. I just didn't write down my repeating ones. So here are all my outputs. I got a 3, a 7, a 3/4, a 3, a 7, 3, a 7, a 3/4, a 3, and a 7. That's almost all my points. The only one that we haven't checked would be f of 0, 0, which is that first point. Well, if I go up to my function, I plug in 0, 0, I get 0. Okay, so that's what we get for all of those. So we can actually pick up a few things. We have the absolute max is anywhere we see a 7. Okay, so the 7s come from, so it's an absolute max of 7 at, okay, we got to write these down. Okay, so the 7 came from 2, 1. That's this one. The here is 2, 1 again, so we're good there. The 7 here is going to be -2, -1. And then the last one is also that same thing. So there's our max. We also have an absolute minimum of, okay, we have 0 at 0, 0. So there, all that work for that answer there. So these are a pain. We have multiple sides that we can do. We can do 4 sides. We could, if we do a triangle, we'd have 3 sides. It gets a little tricky when we make one side curve a bit, but we will cover that in another example.